So what we're looking at today is, again, with these translations, these transformations. So the first thing we're going to be looking at is translations. Now, yesterday, we were given the function with the translation that had happened. It told us that x plus 3 described the translation or the transformation and the parent function. They gave us the graph, or they gave us the equation with the transformations already occurred, with them already have happened. And it's just wanting us to kind of say what they are. Today, we are actually going to be applying the transformations. We're going to be applying the transformations to a function to see what will happen. Now, each one of these translations, we are going to take them one step at a time. We can't do multiple all at once because, especially when we start talking about vertical stretches and vertical shrinks, will affect the entire function. There are certain ones that will affect everything and some that won't. So we have to take it one step at a time, especially if we're doing multiple. Now this here I already provided everything for you, so you don't have to write any of this down. But a horizontal translation of the graph y equals f of x minus h is a horizontal translation of the graph of y equals f of x where h is different from 0. So what we're doing is wherever there is an x, whatever the translation is, we're replacing it with that. And we'll see, it'll make more sense. A lot of what we do in here will make more sense once we start seeing the problem, seeing examples of it. Vertical translations, up and down, the graph of y equals f of x plus k is a vertical translation of the graph y equals f of x where k is different from 0. Does anybody know why it has to be different from 0? What is f of x plus 0? F of x, is it going to change it? No, we need it to be different from 0. That's understood. We know that makes sense because if we add 0 or subtract 0, it doesn't change it. But because, again, this is mathematics and we like to be overly particular, they'll add it in here just as clarification. This does not work. It doesn't do anything. So we exclude it from the equation from this here. Again, we're changing what goes into the function with our horizontal. Vertical, we're changing what comes out. Okay, so let's look at this here, and we'll start looking at these as we go. Okay. Write a function g whose graph is a translation 3 units down of the graph of f. So since we're talking about up and down, would this be horizontal or vertical? Vertical, vertical, vert, up and down, up and down. So when they say g of g, they're really just saying g of x. It's just function notation. H is just h of x. We're just another way to say y, because we want a way to differentiate the functions, be able to tell the difference between the two. I need another way to name it. Now, since we're talking about a vertical translation, what the definition they gave us a minute ago was f of x plus k, whatever that amount is that we're moving it either up or down, that amount. Now, what did they say the amount that we're moving it is? 3 and it's down. So if it's down, it would be minus. Because if we're talking about going down, we're talking about a negative direction. Up is always positive, down is always negative. Right is always positive, left is always negative. So we have this here. And this will be helpful, especially getting used to this here, seeing how the numbers work and how they're going to work together. So down 3 is telling us how we're moving the function. Now what is f of x for us? 2x plus 1, yes? So let's replace it with that function, 2x plus 1. Now we are going to simplify this here. Is there anything outside or in front of that first parenthesis? No, because if there's a number out there, we have to distribute. If there's a sign, we have to distribute it. We don't have to do that, so we can just drop the parentheses. And last but not least, combine like terms. So what are our like terms? 1 minus 3 is? That's it. We have now translated the function 3 units down. Questions on this here before we look at the next part? We good with the first part? Well, obviously the next part is going to be write a function h whose graph is a translation 2 units to the left of the graph of f. So our left and right, I'm going to scroll down a little bit so it's not so low on the screen. So we're saying h of x. Now when we talked about horizontal, moving left and right, what they told us is that this here is equal to f of x minus h. This is just by definition. Now they didn't use h of x, they used y. Y and h of x, y and f of x, y and g of x, those are all the same thing. H of x equals f of x minus. So where are we moving this? So I will have a 2 in here, and it will be what? Negative. Right now it's taking everything in me not to change that. Why is that? It's positive, okay? Because a negative and negative make a positive. If it makes sense and we got that in there clear, we can just leave it like that. If you have a feeling looking back on it, that might be something that'll trip you up, put a note in there, just so you remember. Or we can just, and what I'll do is you don't have to erase this because I'm going to do it. What you could do is leave it as this here and go and just right below. Either way works. Okay. Any questions on this so far? So I wrote that down just so I have it, so I'm not scrolling up and down. I'm getting a little too far away from it. So nothing earth-shattering so far. Okay. So our original function was f of what? X is going to be 2x plus 1. Do I have f of x anymore? What do I have? F of... So that means everywhere there's an x in f of x needs to be replaced with what? X plus 2. Because all this is saying f of x, the variables over here are just putting x. Because if I'd said f of y, it would have been 2y plus 1. That's all it is. Because if we do f of 2, what would be equal to 2 times 2 plus 1? Y'all remember doing that in Algebra 1? It's the same thing. But here we're replacing it with a variable and a number with a sign in the middle. So that means that when I plug this in for x, I will have 2 parentheses, x plus 2 plus 1. Because in our function f of x, we replace the x with x plus 2. We change from f of x to f of x plus 2, which means on the other side, the 2x plus 1, I have to replace that x with the x plus 2. Okay? Well, we can't leave it like that. It looks a little funky. So we'll simplify it. We can distribute the 2. 2 times x is plus 1. Combine those like terms. And we get this here. It almost looks like we just added 4 to the function and got the same thing, isn't it? This only really works with linear functions. Linear functions, the left and right movement do differ a little from what the amount that they move up and down depending on the vertical stretch that has been applied. The left and right and up and down can be made to be the same. Here it's going to be up 4 instead of left 2. But what's our vertical stretch? How far do we move it over? 2 times 2 is 4. Okay. Now when we start talking about quadratics and any other type function, they don't work this well because they're not a straight line. Does that make sense? So, well, okay. Any other questions on this before we move on to the next one? Okay. All right. I have a feeling I'm going to have to break this. I'm not ignoring that. I just know I'm going to have to write over the top of it. My writing on the board's bigger than what that space is. So let's look at this here. Write a function g whose graph is a translation 5 units up of the graph of f. So we're saying g of x is equal to, well, vertical would be our f of x plus k. Well, how far are we moving it? So we would have 5 and it would be positive. Up is positive, down is negative. Now what is f of x? Well, we don't really need the parentheses. So negative 9 plus 5 is? This is how I write it out if I was doing this. Actually, I would have skipped several of those steps, but I don't write out g of x, g of x, g of x, g of x every single time because I know it's holding true. As long as you can keep that kind of straight, that's fine. You don't have to rewrite it. If you want to rewrite it every single time, that's fine. It's not going to hurt. Any questions on this first one here? We good with this here? Okay. Everybody finished writing. Yes? Okay, because I'm going to have to erase it all for x minus 9 to be able to look at this one here. Okay, we want to write a function h of x whose graph is a translation 1 unit to the right of the graph of f. So left and right would be x minus h. So what is the value of h? It would be 1. It would look negative in the overall because it'd be x minus 1, but we're plugging in positive 1 into it. So when we had it move left last time, we plugged in a negative 3. The negative and negative gave us a positive. So here it's just going to be x minus 1. So our function is 4x minus 9. This is our f of x. Well, we don't have f of x anymore. We have f of x minus 1, which means every place where there's an x in this function, it's getting replaced with x minus 1, the whole thing. Questions? So what we would get is 9 times x minus 1, not 9, never mind. 4 times x minus 1 minus 9. Because we're just replacing that x with what's inside the parentheses. And the next thing we would need to do is to distribute. 4 times x would be minus 4 minus 9. Combining like terms would be negative. Okay. And that'd be our answer. Any questions on this here? Okay. And we'd call this h of x. We good with up, down, left, and right? Awesome. Let's look at these two here. These two here I won't, because up, down, left, and right, as long as you keep the notation good, you're pretty good. So what would we say the translation of 3x up 5 would be? Actually, that's it. Because if I use the f of x plus k, it would be f of x plus 5, and f of x is, can I combine those? Because this is 3 x's, this is just 5. We can call it g of x. That's it. Because this one didn't have anything being added or subtracted to x, so there was nothing for it to combine to, we just call it 3x plus 5. You're good. Here, we're moving it 4 units to the right. So if I were using this here, we would say x minus 4. And we replace this every spot x is. Anything to combine? We can't. Because it's inside the absolute value bars, it's stuck. there. Unlike parentheses, we can't just drop the absolute value bars because the absolute value bars are talking about a distance from 0, or distance, talking about distance. So we can't just drop those, we have to leave them. So this is as far as it goes. So there's some cases where you're literally just throwing it in, x minus 4, we're done. We don't have to do anything else to this. Questions on this here? Reflection in the x and reflection in the y. We're going to do both because reflection in the y actually doesn't do a whole lot. Reflection in the x, technically speaking, doesn't do a whole lot. We're not having to really think about it deeply of what we're actually talking about. We'll briefly talk about horizontal translation. We already talked about this. Horizontal stretch and shrink. And I will kind of show you how that works. We're not going to get too deep into it because I've seen it, it's very easy to get backwards. Unlike vertical stretch and shrink is a little more straightforward, horizontal stretch and shrink is very easily to get confused, okay? Because you really have to work with reciprocals of whatever it's saying. So a vertical shrink of 1/4 is actually applied with a 4, not a 1/4. A vertical stretch of 4 is actually applied as 1/4. Does that make sense how in the heck that got backwards? That's why I don't do too much of it, because it's really easy to get flipped. If I'm not paying attention, I won't flip it and I will get it wrong. Okay. Now reflections in the x-axis, because again, when we talked about it yesterday, it is affecting the output. X-axis reflection. Really what we're saying is y equals negative f of x. Reflection in the y-axis, y equals f of negative x. It's affecting the input. Because as we see it here, this makes a little more sense than what we talked about yesterday. Because when we put the number into a function, we input it, it goes in place of the x, yes? Well, I'll draw here. And immediately with that reflection, we just took it from positive to negative or negative to positive. Because of that negative sign, it's changing the sign of the number that we put in. That's affecting what goes into the function. Does that make sense? So on the x-axis, if we think about it, if it was on the right side, it's now on the left of the number we're plugging in. And if it was on the left, it's now on the right. We flipped it across the y-axis. Where here, whenever we're done, the y value, because f of x is y, that should come out. The negative is now taking it from it was positive to now being negative, or if it was negative, it's now positive. So it's affecting the output. And that's really what I meant yesterday when I said it's affecting the input or the output. Can you all see that there? Okay. So let's see how this works. A, write a graph G, write a function G whose graph is a reflection in the x-axis of the graph of f, this here. So G of x equals. So if we're talking about in the x-axis, it's our y equals what? Negative f of x. So negative f of x. Negative, parentheses. Well, f of x is this whole thing here, yes? The absolute value of x plus 3 plus 1. Absolute value x plus 3 plus 1. And again, I always put parentheses whenever I'm plugging something into the function or replacing something, just in case a case like this comes up. In the last few, it really didn't matter. We had one where we had to do some distributing, but some didn't. And I always put it there just so I'm in the habit of doing it. Because of a case like this, or if we have a number out front. Because here, I can't just drop the parentheses and be done. I have to distribute this negative all the way through. Now, when we distribute it to the absolute values first, it does not go inside. It stays outside. So we multiply it by the absolute values, and we also multiply it by the 1. So the 1 would be now and that is it. Okay, I need to fix that. Any questions on this so far? Okay, we're good. So are we good with this here? Yeah? Nothing too big so far? So really, when we reflect it across the x-axis, we're changing the signs. The absolute value doesn't go inside because anything that comes out of the absolute values is always positive. We needed it to be negative. So we leave it out front. The 1 went from positive to negative. And that's it. Again, I'm just writing that down so I have it there for quick reference. If there are no questions on that, we'll look at B. So B wants us to write a function h whose graph is a reflection in the y-axis. So for us, I can spell this right. For us, we're dealing with the y equals f of negative x, because that's the reflection in the y-axis. So for us here, h of x is going to equal f of negative x. That is the reflection in the y-axis. Now our function f of x, y'all have it where y'all can easily see it still. It's not way up above. So what are we doing here? We're replacing x with negative x. So what we have is the absolute value of negative x plus 3 plus 1. Well, I don't really need those parentheses. We can drop those, yes? And I'm left with the absolute value of negative x plus 3 plus 1. That's it. Any questions on this here so far? Okay, I said I would do this the other day so that y'all can visually see how this works. Because up, down, left, and right, I think you're good. Because y'all can hopefully picture a line going up, down, left, right. If not, there's nothing wrong. That's just me assuming wrong. But this here is the starting function that we just messed with. Now the first thing we did was we reflected across the x-axis. As you can see, the whole thing flipped down. And this one here is a reflection across the y. So we can see the mirrored image, and they do share this 0.4 because anything on the line itself is actually shared, is flipped to itself. And we get something like this here. kind of interesting. Now, let's see here, not that, this. Oh, wrong way. Not insert. Delete X. And turn him off. Now I said yesterday sometimes the reflection across the y-axis doesn't do anything. Well, I still have the 2 on, but do we see any difference? Now again, it said a reflection across a line, a line of reflection, is the same distance from the line. The new point and the old point are going to be the same distance across that line. So we're reflecting it across the y-axis, so a point like this right here is a distance of 1, 2 from it, yes? So its new point would be 1. Well, that's exactly on the line itself, yes? And this point is now over there, and this point is now over here. So essentially the points flipped, and the graph of the function is exactly the same. So with absolute values and quadratics, it actually works out that when we reflect them across the line, when it is on the y-axis, where its line of reflection is on the y-axis and it flips, it essentially flips onto itself. So we don't see any change. Any questions on this here? So Malachi, how are we doing? We good? Okay. So does anybody have a guess at what the reflection across the x-axis of this function would be? So it would be the negative f of x, and the function itself would be? Almost. So when we said our new function is going to be negative f of x, yes? So that means we're applying the negative to the function itself. And then we would distribute that negative, which would be negative absolute value of x minus 5 plus 4. Because the one you gave, Anna, would be not x, but the y. Reflection across the y changes just the x's sign. Reflection across the x changes the whole thing. Questions on this here? Feel good with this here? So this one here is across the y-axis. So we're talking about f of negative x, which would be the same thing as saying absolute value of negative x minus 5 minus 4. Well, might as well just say negative x minus 5 minus 4. Any questions on this here? Are we good with this here? we want a reflection in the x-axis. Well, it'd be helpful if I can write. So we're going to be taking negative f of x because it's across the x, so it's negative f of x. So we'll really have negative absolute value of x plus 2 minus 1. Negative and a negative make a, so for the absolute value, we just have the absolute value of x plus 2. Our negative 1 would become and that's our new function. Any questions on any of this here? We good with this here? We want to reflect this in the y-axis. We want to reflect 1/2 x plus 1. So we're going to have f of negative x, which plugged into the function would be 1/2 of negative x plus 1. And 1/2 times negative x is questions on this here? Horizontal stretch and shrink, and I think you already have it written out like this, yes? Because I'm nice and I didn't make you try to write all this out. So let's look at this here. The graph y equals ax is a horizontal stretch or shrink by a factor of 1 over a. Of the graph y equals f of x, where a is greater than 0 and a is different than 1. Multiplying the inputs by a before evaluating the function stretches the graph horizontally away from the y-axis when a is between 0 and 1. And shrinks the graph horizontally towards the y-axis when a is greater than 1. So that means whole numbers shrink, fractions and decimals, or fractions, and anything between 0 and 1 stretches it. So if I had a value, a horizontal movement by 1/2, it would be a what? Stretch. But what I plug in would be 1 over a, which is 1 over 1/2, which would be 2. Anybody lost yet? A little bit? That's fine. Because, again, it's just moving parts because we're good with stretch. Okay, bigger number stretch, smaller number shrink. Here, smaller number means stretch, but then flip and then plug it in. Bigger number for horizontal means shrink, flip it to plug it in. And the reason that this is sometimes confusing is because we're talking about it on a horizontal movement. Because if I'm stretching along the horizontal, means it's moving faster horizontally. So for a quadratic, that would look something like this here because it's increasing faster along the horizontal. But how is it moving along the vertical? Slower. If it's moving slower along the horizontal, close together, it means it's moving faster along the vertical. And they're not interchangeable because they affect different parts of the function. Because as we saw with reflection in the y-axis, when we reflected in the y-axis, it only really affected the variable x. and anything connected directly to it, multiplying by it. Anything addition and subtraction, it didn't touch. So here, when we have f of a times x, that a times x, just like negative x, is really only going to affect that variable. Now, when we look at vertical stretch or shrink, y equals a times f of x. So that's very similar to our reflection in the x-axis, negative f of x. And as we saw with it, it didn't just affect one part, it affected the whole thing. It made every single part, the absolute values and anything being added or subtracted, negative. If we have higher degree functions, it'll make every single part of them negative, or here it's going to affect every single part. And this here is a big reason why the order in which these are done, because when we do more than one, matters. Because if I moved it up or down and then stretched it, that value of the stretch will affect the movement up or down. So a vertical stretch followed by a horizontal movement, moving it up, will be a different function than if I moved it up and then stretched it. They'll have different values. Do you all see that? And it is something that is easily missed. It is very easy to look over it. I'm not talking about because I've seen y'all, no, I've done that. So this is where we'll pick up tomorrow.